So today I'm going to talk about SchrodinText, which is a system that protects the confidentiality of textual content on mobile applications. So there are many applications out there that show some form of textual content, basically some text on the UI for the user to see. For example, consider a bank application which shows users private financial information on the UI, or think about a messaging application that can potentially show very sensitive and private messages to the user. And the same app can be used to show potential authentication codes for two-factor authentication scenarios to the user so that the user can use it and log into some system somewhere. So in all of these cases, it's very important for us to protect the confidentiality of this text. That is, we want the user to see the text, but we want to make sure that no malware in the system can potentially steal or extract the text. So the application developers are themselves aware of the sensitivity of this content, and they can use protection to protect it. They can use encryption to protect it. So let's see how that looks like. Here you can see that all of these applications usually have a front end that runs on the mobile device. That's the right side of the slide. You can see the application on the OS and the display at the bottom. And the other component of the application is a backend that is running in the cloud. And in all of these scenarios, this private and sensitive text always originates in the cloud. Or at least those are the scenarios that we are concerned with. So now let's see how we can protect this. The backend and the front end first have to establish the shared cryptography key. And once they have the key, then the backend can use the key to encrypt the text, and then it will generate the cipher. And then it can send the cipher over the network to the front end. And because of encryption, now we've protected our text against any potential eavesdropper in the network. But now this is where the problem actually starts. So we have a cipher in the front end, but the front end has to first decrypt it. And then it has to pass it to the operating system for it to be rendered and displayed to the user. So then if you have any potential malware on the device, you can try to steal the text by either directly attacking the application and leveraging some of the vulnerabilities in the app, if any. Or you can try to compromise the operating system, and you can try to, for example, escalate some privileges to a kernel, and then you can use various methods to steal the text. So as you can see, the trusted computing base, or the TCB of our system is very large here. It includes the application, the operating system, and even the hardware. So while the application developers can do something about their own application, they can try to make sure there's no vulnerabilities in it. There's nothing they can do about the operating system. And unfortunately, it turns out that today it's quite easy to compromise the OS because it's very large, it's full of vulnerabilities, and there are many reported attacks on it. So we know that the operating system is vulnerable. So what can we do about it? There are two main directions that we can take, and we'll be working on both of them. So in the first direction, we can just try to continue to improve the security of the operating system. We can try to develop, for example, static or dynamic analysis tools to find these vulnerabilities in the OS and patch them. But this is a battle that might take a long time, or we might not even be able to win it eventually. So an orthogonal approach is to assume that the operating system is untrusted, and then try to see if we can use a very small and trusted monitor to provide some select security guarantees in the system. And this is the approach that we're going to take in SchrodinText. So this is how the overall system will look like now with the monitor. You can see on the client side, on the right side, we have this small monitor that sits below the OS, is more privileged than the OS, and it can protect itself from the operating system. Okay, it's back. So in our system, we actually use the hypervisor enabled by the new virtualization hardware on processors, as well as the secure world on trust to realize this monitor. But for the details, please look at the paper. I would like to mention that obviously we're not the first one trying to use a trusted monitor to provide security guarantees. Our own Landon class, I don't know if Landon is here, he has a very nice vision paper in October 2007 called the Pocket Hypervisor, where he argues that we should use the hypervisor on the mobile device to provide security guarantees, as well as other features. So basically, our work is just a realization and demonstration of this 10-year-old vision. All right, so now let's see how our story will look like. So remember that the front end has a cipher, but the main difference here is that the key is shared between the backend in the cloud and the monitor, but not in the front end, because the front end is not trusted. And we require some handshake and some protocol to safely share the key between the front end and the monitor. I don't have time to go over it, please look at the paper for details, but going forward, we assume that that key is established between these two components. So now the front end cannot decrypt the text anymore, which is good because it's untrusted, but it can pass the cipher to the monitor, and then the monitor can decrypt it, and then it can render it and put it on the UI. And also, we'd like to emphasize that we are only trying to provide confidentiality guarantees here. I forgot to mention that now our TCP is much smaller compared to what we had before. It only includes the monitor, which is hopefully a few tens of thousands of lines of code, as well as some hardware. Okay, so as I was mentioning, we're only trying to provide confidentiality guarantees for the text. We do not provide any integrity or availability guarantees, which means that the operating system can try to show some other text that the one that is intended, or it can try to show no text at all. Those are orthogonal issues that has to be solved in the future. All right, so let's see if we can actually even solve the confidentiality problem. The problem is that in practice, doing this text rendering in the monitor is quite challenging. So let me show you what that will include. So I'm going to show you the different stages of text rendering that now has to be done on the monitor. So the monitor has that text, which is now a string. And the first stage of text rendering is to rasterize the character points. Basically, it has to generate the pixel level information for different characters, given the font and the size. And for example, it will tell us that this is how C will look like, this is O, this is B, etc. Once those widths are rasterized, the next stage is to do the layout. It has to decide where on the UI each of these characters will go to. And this is also challenging because the layout depends on all the other elements on the UI, their size, and the size of the UI surface, etc. And you can see that we're already adding a lot of code to the monitor, and we're not even done yet. The next stage is to do compositing, to composite all of these data on top of each other. And as it's done on mobile devices today for good performance, we would like to also use the GPU for acceleration of the compositing. And therefore, we will need to add the GPU device driver and the libraries in the monitor as well. So before we know it, we've added about 500,000 lines of code to the monitor. Now the monitor is bloated, its potential to flow vulnerabilities can be attacked and be compromised, and therefore this has completely defeated our original purpose. So our main contribution in this work is to come up with a set of techniques which we call the Multiview text rendering, which allows the operating system, which is still in the untrusted domain, to do most of the text rendering, and we only have to add about 1,000 lines of code to our monitor to do some very simple processing. So I'm going to show you how this Multiview text rendering technique works. I don't have time to go over all of the stages. I will just cover the first two. And for the rest of it, please see the paper. And so let's first get started with the glyph rasterization. So to remind you, the problem is that the operating system doesn't know what the text is, so therefore it doesn't know which characters to actually rasterize. So our solution to this problem is to have the operating system rasterize all the printing ASCII values, which are there about 95 of them. And given the font and the size and the color, put all of them into what we call a glyph book. It's basically just an array memory buffer. So therefore, the operating system can tell us this is how an exclamation mark would look like. This is the equal sign. This is 0. This is 1, etc. And then we can share this with the monitor. So note that the limitation is that we're only supporting this ASCII characters. We do not support, for example, emojis or non-English characters at this point. And that is something that can be added. Alright, so the next stage is to do the layout. You always have to tell us where to put each of these characters on the UI. But this is difficult because the operating system only knows the number of characters in the text, and the number of characters is not necessarily enough for it to do the layout. So let me show you an example. These examples, all of them have 9 characters. But as you can see, they're taking up a different size on the UI, and this is mainly because the different characters are taking up different width. So therefore, there's no way the operating system can actually correctly do the layout. So our solution to this problem is to focus SchrodinText on monospace fonts, which are actually quite common on mobile devices. With monospace font, the property is that all of the characters will take up the same amount of width, no matter what the actual character is. So therefore, now the OS can go ahead and do the layout without knowing what the actual text is. So let me show you an example. Let's say we ask the operating system that please go ahead and lay out 9 characters. The OS knows everything else. It knows the dimensions of the UI surface. It knows where that text UI widget is on the screen, which we call it the SchrodinText provider, which is based on the text technology. And then therefore the operating system can decide that, okay, the first character will go here, and then here's the second one, and here are the rest of them. and then it will share this layout information with the monitor. And remember that the monitor already has the glyph code, and therefore it can do some very simple jump off of blending to resolve these characters. So it will put the C here, and it will put the O here, and so on. So this is a very simple example. In practice, if the length of the text is larger, then we have to worry about line breaks, and we have some solution for that as well in the paper. We do some hyphenation. It's a very simple layout technique, and we cannot, one of our limitations is that we cannot support fancy layout algorithms such as Textual. All right, so I'm not talking about different components of this text rendering, but there is one more technical component. I want to talk about one specific attack that the operating system can mount on our system. So, and this is called the framebuffer readback. So what the operating system can do, it can wait for the monitor to show the text on the framebuffer, and then it will just go ahead and simply take a screenshot and see what it actually put there. And you can see it. So to protect against this, we use some of the novel hardware features that are available on processors and also on SSD as part of the virtualization support, including hardware reviews and the nested page tables. More specifically, what we do is that for those memory pages on the frame buffer that have some sensitive text on them, under the we actually keep two copies. There is one copy which we call the protected view that has all the UI elements on it and the text blended on top of it. And then we have the unprotected view, which has all the UI excluding text. And then we map the protected view into the IO view, which is sitting in front of the display controller, so that the display controller can actually read the correct frame buffer content and put it on the display for the user to see. That's our goal. And then we map the unprotected view into everything else in the system. So we map it into the MMU for the CPU, which is running the operating system. We map it into the IO that you see in front of the GPU or any other DMA capable device. So if any of those components then try to actually see the frame buffer, for example, take a screenshot, then the text will somehow magically see. Alright, so we prototype this on ARM Juno development board. This is the only board that we found that allowed us to program the secure world of TrustZone and also the hypervisor. We use Android Marshmallow running on top of the same hypervisor, and we use the OpenTE for our secure world router. So I'm going to show you some evaluation results right now. I don't have time to go over all of them, but I'll just refer them for the rest of the paper. So first, I'm going to show you some security evaluation. I want to show you that our system can actually defend against the UI frame, the frame buffer readback attack that I mentioned. So here's an actual demo of SchrodinText. So here you can see the display that was connected to the Juno board, and we're using SchrodinText to, it's a very simple app to put to basically render some text. And this is basically what the user physically sees on the display. So what we've done here is taken a camera, external camera, and take a photo of the display. So now at the same time, we try to use the operating system with all its privileges to try to take a screenshot with the frame buffer. And as you can see, all the components of the UI are there, including the Android notification bar and this virtual keys at the bottom of the screen, but the text will disappear. Alright, so the next component is the performance, and for that we mainly measure the text rendering latency. And that is basically the time it takes from when the application says render until the time you're done with the rendering. On the x-axis, you can see different number of characters on the UI that we're trying to protect. And just a quick practice is you don't have to protect all the text on the UI, just the ones that you care about. And on the y-axis, you see the latency. So as you can see, if you're only trying to protect a few number of characters, so for example, a single code, then the latency is not that different from the normal language text. But if you're trying to fill out the UI with full of protected text, then obviously the latency is going to be very significant. Alright, so before I wrap up, some of you might be wondering where the name SchrodinText comes from. So it just simply comes from an analogy to the Schrodinger's cat that we had in mind. So as some of you might know, this is basically a thought experiment in quantum mechanics where there's this cat in the box, and the box is closed, and it can be simultaneously dead and alive. And so when you have an external observer that opens the box that can see actually the actual state of the cat, it would collapse in time. And so you think of the text in SchrodinText as this cat in the box. So from the operating system perspective, you just see that there's a 9-character text sitting somewhere on the UI, but it doesn't know what the actual value is. So only the user who can open the box by physically observing it at the display can see what the actual value is. All right, so in summary, SchrodinText helps us render sensitive textual content of applications in the UI, and it can help us protect it against the operating system and malicious application. It has a very small TCP, and also it has noticeable performance. All right, so that will conclude my talk, and I'll be happy to take your questions now.